this. Growth model and direction fields, we did this together as an example. So say here is our population growth model. Now this is the way I originally talked about the logistic model. 1 minus P over M, if you recall. Here, that is N is 1,000. Okay. So just to refresh our memories, let's sketch the solution curves corresponding to these given initial conditions below. So if P of 0 equals 100, well, that's the initial condition we had. Oops, sorry, 100. 100 is right here. What would the curve look like, the population curve? Well, we just follow these guideposts. It's increasing at an increasing rate, then what happens? All right, slow down. What if, on the other hand, the initial condition was P of 0 equals 1,000? What do you notice? Yeah, if I look at this, it's kind of hard to tell where does it go. Is it downward? But if I go down, it tells me to go back up again. What if you put P equals 1,000 in that differential equation? What do you notice about that expression, or the factor on the right?
0.
1,000 over 1,000 makes a 1. 1 minus that? 0. Zero's out the derivative. And if P prime equals 0, then guess what?
0.
That's it. It remains 0. This is what's called a equilibrium solution. Yeah. And we'll talk about that as well today. What about P of 0 equals 1,400?
Drop.
Yeah, 1,400.
All roads lead to 1,000.
Looks like it. Looks like it. Now, so for that reason, we did talk about that 1,000 a little bit. That's a special number. That's what we refer to as the carrying capacity. If somehow the population got above that, it would drop, right? Okay. So that 1,000 is a sort of limiting number, limiting capacity, carrying capacity. Okay. Now, what I want to show you is that we can rewrite this. This is another form of the logistic, but what I'm going to do is factor out, I'm going to factor out a 1,000. Or I'm going to multiply that by 1,000, and to compensate for that, I'm going to divide this by 1,000, and then this would be 1,000 minus P. Okay, 0.08 divided by 1,000 is just that's just 8 times 10 to the what? That's another 10, that's 8. Negative 2, and negative 3 more, negative 4. So this is the form that we just saw. Okay, and there's a constant. Okay. So that 1,000 is an M. You can see it alternately in this form, M minus P, or in this one, 1 minus P over M.
Oh, fine.
You dropped a P.
Oops, I did. There's a P out front of that. Okay. All right. So yeah, we have this 1,000. That's called a equilibrium solution. Okay, because if it ever hits 1,000, then the growth rate dp dt is just 0. Right? If I put P equals 1,000, we get 0 growth. So flat lines. Are there any other equilibrium solutions? 0?
Yeah.
Right. If P is equal to 0 in this equation, you get 0 times 1, right? 1 minus 0 over 1,000. You'd still get 0. Okay. Right, and you can see this down here. And that one, this one does make physical sense, right? Because if the population hits 0, is there any way for it to increase after that?
It's the same as 1,000.
Mutation.
Depends on when we're talking about a population of amoebas or a population of human people. Okay, so we got these what's called equilibrium solutions. Okay, that's a good place. That's a good place to take a break. So notice, yeah, equilibrium solution at 0 as well. If the population hits 0, it stays at 0. If the population is at 1,000, it stays at 1,000. Okay, when we come back, we're going to distinguish between, well, there is a qualitative difference between those equilibrium solutions. We'll talk about that.
What about cases where like starting close equilibrium
Right, that's not accounted for in the model. That couldn't happen. Yeah.
what we have to do is make a model?
Oh, God. Some other term, I don't know right off the bat.
There's some war in there.
All right, let's we'll take a 10-minute break. If you've got a question, Dan, go ahead.
Like minus 1,000 population.
Start at 2:50.